In the previous lecture, we introduced both the geographical and the celestial coordinate systems. And now, we are ready to calculate the position of the Sun for a specific location on Earth at any given time and date. The final goal is to obtain the altitude and azimuth of the Sun, and we will first use a flowchart to explain you the procedure. In the last couple of slides, we will also introduce you the Analemma, which is obtained from the altitude and azimuth of the Sun. First step is to locate the observer position on the Earth crust, and thus the PV system, by means of the geographical latitude phi and the longitude lambda. In this case, we have Delft, that is located 52 degrees north and 4 degrees east. We also need the moment of the day in which we want to calculate the position of the Sun. So we have to provide the date and the time. Finally, the last input parameter that we need to know is the axial tilt, Epsilon, which is the angle between the north ecliptic pole and the north celestial pole. This angle is not constant, as it has cyclic oscillations between 22.1 and 24.5 degrees, and it is function of the date. The first operation to perform is obtaining the local mean sidereal time, shortened in LMST and represented with the theta L. Looking at the picture where the Earth is seen from the North Pole, the local mean sidereal time is the angle between the vernal equinox, which is used as a reference, and the observer meridian in green. LMST is a way to keep tracking of the time based on the sidereal day, which is the duration between the two passes of the vernal equinox through the observer's meridian, and it is slightly shorter than a solar day. Its duration is approximately 23 hours and 56 minutes. In the same picture, also the longitude of the location is shown in red, since, together with the date and the time, it is one of the inputs to calculate the local mean sidereal time. In the orange box of the flowchart, the ecliptic longitude of the Sun is computed, as depicted on the right-hand side. Remember that the ecliptic is defined as the path of the Sun in the celestial sphere. Therefore, the red circumference is the path of the Sun with the Earth in the center. As a consequence, if we want to indicate the Sun position with the ecliptical coordinates, then the altitude beta of the Sun is always null. So this orange box represents the equation to calculate the ecliptic longitude lambda s of the Sun, given the date and the time. In other words, it measures the angular distance of the Sun along the ecliptic from the vernal equinox. Finally, we have all the information to compute the altitude and azimuth of the Sun. We will not show you the demonstration here, since it is beyond the scope of this lecture. However, if you want to give a look to all the steps to get a deeper understanding, please refer to the Appendix E of the Solar Energy book. Once again, the observer is our PV module, and currently is flat on the ground, and we have the Sun that is our object, characterized by an azimuth and an altitude. Its azimuth and altitude are expressed by trigonometric formulas that come from two coordinates changes, from the position of the Sun in the space to its position with respect to the observer, and the whole process entails multiplication of matrices and also trigonometrical calculations. In general, what is needed to be done is to consider the position of the Sun in the ecliptic longitude and altitude, transfer them to declination and the right ascension, and finally to azimuth and altitude of the Sun with respect to the module. Once again, related formulas come from two changes in coordinate. We advise you to go through the appendix in our syllabus to see all the involved steps. Now that we know how to calculate the azimuth and the altitude, it is possible to trace the analemma. In Greek language, analemma means the pedestal of the sundial, and it is a diagram that indicates the position of the Sun when observed at the same time every day. Indeed, due to the Earth's axial tilt and the orbital eccentricity, the Sun will not be in the same position in the sky at the same time every day. In the analemma of the Sun, you may also notice astronomically important days of the year, such as the solstices and the equinoxes. It is also possible to photograph the analemma, as shown in the picture on the right, by just keeping a camera at a fixed location and orientation and taking multiple exposures throughout the year, always at same clock time, resulting in this characteristic shape similar to number 8. To recap, in this lecture we have seen how to calculate the solar altitude and azimuth as seen from an observer, the PV module in our case, starting from the coordinates of the location, the date, the time, and the axial tilt angle. Then we use the sun coordinates to see the position of the sun in the sky at a particular hour, noon in this case, for the whole year, and the output is this H-shaped curve called analemma.